Can you see the screen or the PowerPoint?
Yes.
Yes.
Okay. Gauss elimination method. So in this method, we will learn about the solution of the linear equations, the system of linear equations by the method which is called as the Gauss elimination method. So this type of solution can be performed by hand calculations as well. For example, for 3 or less equations, it is possible or it is convenient to do this type of solution by the hand calculations. So we have a few options for that: graphical method, Cramer's rule, method of elimination, and then for larger set of equations, we can use the computer methods. Okay, so first to illustrate the graphical method, if we have two equations, a11 x1 plus a12 x2 is equal to b1, where x1 and x2 are variables, linear variables, and a11, a12 are the coefficients of the linear variable, and then b1 is the coefficient, the constant on the other side. And similarly, we have the second equation as a21 x1 plus a22 x2 is equal to b2. So if we want to solve these two equations for the values of x1 and x2 by the graphical method, one way is to represent these two equations, this equation and the second equation, in their linear format. So that means we represent them in x1 and x2 axis. So for example, we can take x1 as the horizontal axis, x2 as the vertical axis. So in order to represent in their graphical format, so we can represent each equation as something like this. x2 will be minus a11 over a212 plus b1 over a12. That means we take a12 x2 on the other side. Sorry, a11 x1 on the other side, and then divide by a12. Okay. And similarly, for the second equation, we take a21 x1 on the other side, and then we will divide by a22. So we will have the equations in the form where we have x2 on one side and x1 and the other terms are on the other side. So this type of form of the equation is the slope of the line. So in which a11 over a12, that will be the slope, a21 over a22 will be the slope, and the intercept on the x2 axis will be b11 over a2. Okay, so this can be plotted, and then the intersection of these two lines will be the solution. So this can be seen with the help of this example. Okay, so problem statement. So use the graphical method to solve 3x1 plus 2x2 is equal to 18 minus x1 plus 2x2 is equal to 2. So as a first step, then you will represent it in the form of x2. So you will take 3x1 on the other side and then divide by 2. So it will be divide by 2, that is 18 by 2 is 9, and 3 over 2 x1. So x2 is equal to minus 3 by 2 x1. So that will show a negative slope. Okay, so negative slope. So therefore, we will get a straight line like this. That means as we are going from left to right, the the line will decrease from top to bottom. Okay, and which when plotted in figure 9.1 is a straight line with with an intercept of 9. That means it will intersect the x2 axis at 9 and with the slope of minus 3 by 2. Similarly, for the second equation, we can write it as 2 plus x over 2. Okay, so that will be 1 over x, and then 2 over 2 will be 1. So this will be an equation, and this will be a curve with an intercept of 1 and a, a slope of 1 by 2. So this will be an increasing curve, but increasing at a much uh, milder rate than the previous one. The previous one, the slope value is high, but in the negative side. But here the slope value is less, but in the positive side. So here you can have this. So this is the plot for the second curve, and this is the plot for the first curve. And the point at which these two lines are intersecting, this is the solution. So these two lines are intersecting at in x1, so the value of x1 is equal to 4, and for the value of x2 is equal to 3. So 4 and 3, these are the solutions of the this system of two equations. So very simply, this is the graphical method for solving the system of two equations. So the intersection of the two equations is the intersection of these two equations on the graph is the solution of the curve, which can be represented very easily on the graph. However, in this case, we have a few variations. Few variations can happen, and then these variations can cause us some problem. So one of the variation is that we have one equation whose plot is like this, and we have another equation whose plot is like this. As you can see that these two lines are not intersecting with each other. Okay, they are parallel. So since they are parallel, they are not intersecting with each other. Therefore, these two systems of equations will exhibit no solution at all. So if we will try to solve them numerically, then we will not get any solution at all. Similarly, here we have two lines. One of the line is this, and the other line is this. The other line is simply a multiple of that line. So when we will plot these two lines, and these two lines will be coinciding with each other, which means that they will have infinite number of points of intersections. Okay, and this means that this type of system will have an infinite number of solutions. And similarly here, and but not similarly here, but here we have some these two lines, but these two lines are intersecting with each other, but at a very small angle. It means they are quite different. They are not very much different from each other. And then in this case, it is very difficult to see where exactly these lines are intersecting with each other. Although numerically it may have some more accurate solution, but visually we can see that we cannot say. Someone will say that it will intersect at this point, someone will say that it is intersecting at this point, someone will say that it is intersecting at this point. So graphically it is difficult to see the solution. And then we see that these equations, so these equations are only slightly different in number. So for example, instead of 1 by 2, we have 2.3 over 5, which is also nearly 1 by 2. And instead of 1 over here, we have 1.1 in the equation over here, so which is very close to each other. So this type of system of equations is called an ill-conditioned system. That means where the change in slight change in one variable may cause a large change in the solution of the system. So these kind of problems may arise. Next, we have the determinants and the Cramer's rule. So a determinant can be illustrated for a set of three equations. So uh, by the definition of the determinants, if we have the set of three equations, so for example, if we can represent these equations by their coefficients in this matrix form, okay, so these are the coefficients of the three equations. So a11, a12, a13, all are respectively being multiplied by x1, x2, and x3 if we have a set of three equations. So the set of coefficients, if there are set of coefficients of x1, x2, and x3, can be represented by this matrix, and then that matrix is multiplied by this a vector of x values, then that will be equal to the vector of the b values. So this matrix A is the coefficient matrix. So assuming all matrices are square matrices, there is a number associated with each matrix A called the determinant D. So for each matrix, each of such matrix A, we can say that there is a number. Okay, there is a number. That number is called as D. Okay, so how we can determine this number D, that is the determinant? This can be determined, for example, if for the matrix has just one number, A11, so that determinant will be that number itself. But for a square matrix of order 2 and 3, there are certain there is a certain method to determine the determinant. Okay, so such as uh, for a coefficient matrix of say 2. Okay, so the determinant will be determined of the for a coefficient matrix of order 2. So the determinant will be found by multiplying by the uh, diagonals. So for example, if we take A22, then we will multiply it with A33, and then we will subtract the other diagonal, the product of the other diagonal. So A22 minus A33. So in this way, you can determine the determinant of 2 by 2 matrix. For the 3 by 3 matrix, such as shown over here, if we want to do the find the determinant, so then what you will do is you will apply this process sequentially. So you will take the first row. In the first row, you will take the first row and first column element, which will be A11. So if you, in that case, if you will eliminate A11, A12, and A11, A21, A33, and then the remaining matrix will be the minor of the matrix. Okay, so that D11 we can write corresponding to A11. We will write a minor matrix D11, which will be A22, A23, and A33, A32, and A33. Then you will take A12 for corresponding to A12. So you can strike out this first row and then this second column, and the remaining matrix will be A21, A23, A31, and A33. So for, and similarly you can find for A13 as this matrix. So here now you can see that we have these three minor matrices, and then for each three minor matrices we can very easily find their determinant. Okay, and once we find their determinant like this, and then we can multiply these values by their respective cofactor A11. Okay, so in this case A11 will be multiplied by this minor, A12 will be multiplied by the other minor, and A13 will be multiplied by its minor. And you can see that there is a negative sign in between. So the sign will change alternatively from plus, minus, and plus. So in this way, you can find the determinant. So Cramer's rule actually expresses the solution of a system of linear equations in terms of ratios of the determinants of the array of coefficients of the equations. So what is the Cramer's rule? Cramer's rule is a way of representing the solution of the equations in terms of the ratio of their respective determinants. So in this case, the solution of x1 will be the ratio of these two determinants. So this determinant d is the determinant of the main coefficients, okay? That is this one, okay? And whereas there will be a determinant, and that determinant will be in the denominator. Whereas the other determinant, which will be corresponding to x1, and that determinant will be obtained by replacing the first column of the determinant A with the values of B1, B2, and B3, with the values of B1, B2, and B3. Okay, and then in a similar way, this determinant in the numerator will be found out.
Bless you.
Thank you. Thank you. Okay, so that was the determinant. Okay, so since actually we have already covered this topic in the linear algebra, but somehow this topic is also included in this course. So we have to, anyway, we have to cover it. Okay. Cramer's rule. So as an example for the Cramer's rule, we can take these two equations, 3x1 plus 2x2 is equal to 18, and then minus x1 plus 2x2 is equal to 2. So if we want to solve it by the Cramer's rule, so we will first of all find the determinant, 3, 2, minus 1, 2, and then you can see that its determinant will be 3 times 2 is 6 plus 6, and when minus 2 times minus 1, that is plus 2. So 6 plus 2 is 8. And then in the second case, so in this case, the determinant is of the determinant of this system of two equations is 8. In the second case, we have this equation, minus 1 by 2 plus 1 and minus 1 by 2, 1. So its determinant, you can see that minus 1 by 2, 1 and minus 1 by 2, 1. So if we multiply this, cross multiply this like this, in this way and that way, then what we will get is 0. So as you can see that in this case, there is these two lines are parallel to each other. So we found that their determinant is 0. In this case, you can also see that their determinant is 0. So in the case of 0 determinant, then you can see that there are either no solutions or infinite number of solutions. And in this equation, and when we find out that, so it is minus 1 by 2, 1, and then minus 2.3 over 5, 1. So if we find its determinant, you can see that this determinant is minus 0.04. It is not 0, but it is also not very much different from 0. So for this, earlier we have said that this is an ill-conditioned system. So for that ill-conditioned system, the value of the determinant is nearly 0. Okay, so how to apply the Cramer's rule to solve this system of equations? So it is 0 0.3, 0 0.52, and then 1, 0 0.5, 1, 1.9, 0.67, 0 0.1, 0 0.3, 0 0.5, minus 0.44. So if we want to find the solution by the Cramer's rule, so what we have to do is we have to find its determinant. So the determinant can be written as like this, okay? So 0 0.3, 0 0.52 and 1, and 0 0.51, 1.9, and then this, that means all the sets of coefficients. Remember that for the determinant we use the straight lines. We use the straight lines, but for the matrices we use the brackets. So it's mine. First of all, for the hand calculations, first of all we will find the minors. So the minors are this. So first one will be this matrix, okay, and its determinant will be this minus 0.07, and the second one is this. So you can see that second one will be 0.5, 1.9, 0.1, and then the third one will be 0.51 and 0.1 and 0.3. So this is the determinant, and then this is the determinant for the third one. So you can see that all the three determinants which we have found are very close to 0. Okay. So what is the determinant for the overall matrix? So the determinant for the overall matrix will be 0.3, 0, minus 0.52, and 1. So these are the values from the first row. 0.3 multiplied by this value, and minus 0.52 multiplied by the second value, and then the third one is 1 times 0.5. And we add up together, then we find that its determinant is minus 0.0022. So the determinant is minus 0.0022. And then the next step is to apply the solution. So x1 will be the determinant of this divided by this. So it will be minus 14.9. Okay. And for the second one, the determinant of the second one will be minus 29.5. And then you can see that the solution for x3 is 19.8. But you can see that in this case, each time we have to find the 3 by 3 determinant. So it is very much time consuming to find the solution of the equations by the Cramer's rule or by the method of determinants. Here I can, what you can see is that, well, this is just a simple example, okay? And then this simple example shows a kind of like a very ill conditioned system. So we will look at the state of the ill conditioned system later on in another example. By the ill conditioned by the ill conditioned system, what I mean is that if we, for example, make some slight changes into the equations. So for example, if we say that instead of this factor 0.52, I take it as 0.5, okay? And instead of minus 0.01, I just take it 0 over here. Or what else? Maybe instead of 1.9, if I take 2 over here, and if I take instead of 0.67, I take 0.7. So very close values over here. And similarly, maybe I can change instead of minus 0.44, I can change minus 0.4. So only slight changes in this system I will perform. And by the slight changes in the system, maybe we can see that there will be a drastic change in the solution as well, in the solution. So that's the type of system will be called as the ill-conditioned system. So here we have found their solution. This is the solution for the original system, but solution for the ill-conditioned system will be very much different. Okay, so maybe we can see it with the help of in Excel as well. So for example, let me see what is the system. Okay. So for example, I have this system 0.3. Okay, if I want to represent in Excel, it will be, I will represent it with the help of its uh, coefficients. Okay, 0.52 and 1, 0.5, 1, 1.9, and then 0.1, 0.3, 0.5. Okay, and then it is minus 0.01. Okay, and 0.67 minus 0.44. Okay, so yeah, so in this way I have represented this equation: 0.3, 0.52, 1, and minus 0.01, and 0.5, 1, 1.9, 0.67, and then 0.1, 0.3, 0.5, minus 0.44. Okay, so now I can represent this system. Okay, so what will be x1 for this system? X1 will be, okay, x1 will be equal to determinant. So for there is a command for the determinant actually. So m determ, okay, m determ, okay, of, so yeah, and maybe you can do it step by step. Okay, it's better. So for example, for the first determinant, what will be the determinant? For the determinant D, we should have these values. Okay, for determinant D1, we should have, for example, uh, same values. Determinant D2, sorry, D2. Yeah, D2. So, and then we should have the same values. And determinant D3, we should have the same value, but with difference, okay? So we have these determinants. So, but in this, we have these values of B. So determinant D1, this first column will be replaced by these values. And in the determinant 2, this second column will be replaced by these values. And in the determinant 3, the third column will be replaced by these values. Okay, so in this way I have written down the determinants. Okay, make some space between these three values to, so that it is easy to write. So I am just applying the Cramer's rule. Okay, so what will be the determinant of this? So let me write down the determinant of this is m m determ. This is the command for the determinant in the Excel. So I will select the determinant and then I close. So it is minus 0.002. And now, what is the determinant over here? So this is the determinant for this, okay? And they similarly copy, and then I just copy and paste. It will automatically find this formula, okay? Where is this? Paste. Okay, so now what will be x1? So x1, x2, x3. Okay, so what will be x1? X1 will be equal to this value divided by this value, okay, which is minus 14.9. X2 will be equal to divided by this value divided by the main determinant, it is minus 29.5, and X3 will be equal to this value divided by this value, so it will be 19.8. So I think we got the same answers before. Yeah, minus 14.9, minus 29.5, and 19.8. Yeah, these were the values. But suppose if now I do some slight changes, okay, in this, okay. So if I do some slight changes in this, so for example, maybe I just add some. Okay, so if I have like this, then yeah. So if I do some slight changes, instead of 0.52, I put 0.5, 0.5 here. And instead of minus 0.01, I have 0 here. Okay, and instead of 0.5 and 1.9, I can have maybe 2. And 0.67, I have 0.7, only slight changes. 0.1, 0.3, 0.5, instead of minus 0.44, I can have minus 0.4. Okay, so not much changes. So in this case, I have this equation. So maybe I can copy it. Control C, Control V, Control V, Control V, Control V. And then this one, Control C is, yeah, I cheat. Control V. No. I need to change. Yes, this is 0.3, 0.51, 0.512, 0.1, 0.5. And now I take these values, Control C, then Control V, Control V. Oh, no, not here.
The second column.
Yes, second column. Control C and Control V and Control V. So now I can see that now the solution is this, minus 7, minus 15, and 19.6. Okay, so solution is not the same. So instead of minus 14.9 is minus 7, and instead of minus 29.5 is minus 15, and instead of 19.8 it is 19.9.6. Yeah, it looks like the solution has become, all these values of the solution has almost become half. Yeah. So you can see that this is although the original system is not much difference from the given system. Okay, so because we have just actually rounded up and rounded down certain values, but there is a drastic difference in the solution of the system. So this is an example of a ill-conditioned system. So later on, there will be another example of the ill-conditioned system. Okay, the next is the method of elimination. Okay, so that previously it was the method of the determinants, that is the Cramer's rule, but this is the method of elimination. So in this case, the basic strategy is to successively solve one of the equations of the set for one of the unknowns. and to eliminate that variable from the remaining equations by substitution. The elimination of unknowns can be extended to systems with more than 2 or 3 equations. However, the method becomes extremely tedious to solve by hand. Okay, so in this case, use the elimination of unknowns to solve this equation. So 3x1 plus 2x2 is equal to 18 minus x1 plus x2 is equal to 2. So I think you are very much familiar with this method. So first of all, by the elimination method, you will find x1. So this x1 can be found out by multiplying this by the equations, okay? 2 into 18 minus 2 into 2 divided by 3 into 2 minus 2 into 1. And then it can be very easily be solved. So for example, in this case, in the denominator, we have 3 into 2 minus 2 into minus 1, okay? So this is the same thing in the denominator. And it's just like, it is just like the Cramer's rule, okay? Then we have the naive Gauss elimination method. It is an extension of the method of elimination to large sets of equations by developing a systematic scheme or algorithm to eliminate unknowns and to back substitute. As in the case of solution of 2 equations, the technique for n equations consists of 2 phases: forward elimination of unknowns and then the back substitution. So in this method, you have this system of equations, and then this system of equations is by the forward elimination is converted into this kind of system of equations. This is the triangular system of equations. But by this triangular system of equations, we can use the back substitution method to find the solutions of x3, x2, and x1. So for example, in this triangular substitution, is A33 will, and then C3 will be uh, will be compared with each other. So x3 will be equal to C3 double prime divided by A3 double prime. So here you can see that by this successive method, you will see that there will be a change in the system of the equations. So first row will remain the same. There will be elements that will be eliminated. So A21, A31, and A32 will be eliminated, where there are the elements A22 and A23 will change one time, and this last element A33 will change 2 times. So that's why these uh, single primes and double primes have been shown over here. So qualitatively, this method has been described here. And by the back substitutions, you can find you can find these successive equations for the solution. So first we will find x3, then you will find the value of this x3 to find the value of x2, and then we will find the values of x1 by the values of x2 and x3. So this is the back substitution. Example. So this is the by in this example 3x1 minus 0.1x, and then this. So carry these 6 significant figures during the computation. So first part of the procedure is the forward elimination. So multiply this equation by multiply this equation, this first equation by 0.1 over 3. Yeah, it will be multiplied by 0.1 over 3. Why? We have to remove 3 from here, and then we have to multiply it by 0.01 so that this first coefficient will be come equal, and subtract the results from equation 9.5.2. So we will subtract it from this equation. So in this case, x1 will be eliminated, and then we will have the values for this, for x from x2. Okay, and in this way we will have this. And then but in the second step, so in this case, the first equation will remain the same. The second equation will change, and the third equation will also change, because we have done the same thing with the first equation, but in that at that time we have uh, multiplied the first equation by uh, 0.3 and divided by 3, and then added it into the second equation. So in this case, we get this type of equation, okay, 70.1615. And then we will complete the forward elimination, and then x2 must be removed, okay. So in this way, we get this set of equations, and then we perform the elimination method. Okay, so maybe it is better to do it hands-on. So let's try it on Excel. Okay, although it's very simple to do, but let's try it on Excel. Here, so we have x1, x1, x2, x3, and then we have the b coefficients. Okay, so 3 minus 0.1 and minus 0.2, 7.85, 0.1, 7 minus 0.3 minus 19.3, 0.3 minus 0.2, 10, and 71.4. Yes. 3 minus 0.1 minus 0.2, 7.85 minus 19.3 minus 0.3, 7.1, 0.3 minus 0.2, 10, and 71.4. Okay, so now we want to use the naive elimination method, okay? Not the Gauss elimination, naive method, naive Gauss elimination method. In this case, we will be not using that pivoting technique, but we will just using the naive technique. So in this naive technique, so first of all, what we will do is the first row will remain the same. Okay, first row will remain the same. So I just copy it like this. Okay, the first row remain the same. And now what we will do is we will we will subtract the first row from the second row, but in what way? What we will do is we will take the second row and then minus 0.1 divided by 3 times the first row. Okay, so in this way I will get a 0 over here, and then this will be the value. Okay, and in the second row, what you will do in the third row, what you will do is I will take the third row minus 0.3 divided by 3 times the first row. Okay, so in this way I will get a 0 over here, and then I will get these coefficients. So in the second iteration, now I will have to eliminate this. So in this case, I will first I eliminated these two. values. That means 0. And now in this round, I will eliminate this value. Okay. Okay. And then what I will do now in this second iteration, the first row will remain the same, and then the second row will also remain the same. Okay. Second row will also remain the same. Okay. And now in this case, what I will do is now I have this value. Okay. And I have to eliminate this. Okay. I have to eliminate this. So for the elimination of this, what I have to do is I have to take this value and then subtract it subtract from this value minus 0.19, okay, divided by this value, that is 7.003, okay, and then times this value. So I will get a 0 over here. So I will copy it over here. So in this case, I will get divided by 0. Why? Oh, okay. So yeah, no. I will. This is a mistake over here. In this case, because the value which I am taking is that it should be the constant value. Okay, not this value. Okay. So in this case, now what I will do is the value which I am dividing over here, I should make it a constant. Okay, so that it will not change. So copy and then paste it here. Now it is 0. Okay, and now I will. So it is like this. Okay, so these are the two steps. So now if I want to find x3, okay, so x3 will be equal to this value divided by this value. So it will be 7. Okay, so yeah, we get a crisp 7 answer over here. Yeah, we got a 7 answer. Okay, and similarly, if we want to find x2, so x2, how can we find x2? We can find by the back substitution from this. So for x2, what we will do is I will take this this value minus, because now we have this value already. So minus this value multiplied by the value of x3, and then whole divided by
x3 should be 7, I guess.
Yeah, I think I'm making some mistake. Okay, so it should be sorry, this one. Yeah, x3 should be 7. Yeah, and now I want to find this value. Okay, so for this value that is x2, what I need to do is I will take this value and minus this value times x3 and divided by this value. Okay, so it will be this value minus this coefficient times x3, that is the Yeah, this one, x2. So, and then this has to be enclosed into the bracket and then divided by this value. And then that will be minus 2.5. So it is, yeah, minus 2.5. And similarly, x2, x1, okay, x1. So for x1, what I will do is I will take this first value. So I will take this first value and then subtract it, this value multiplied by x3, and then I will subtract it, this value multiplied by x2, and then close the bracket, divide by, and then divide by 3. So I will get this value, that is 3. That is 7. I got 3, but here I got 7.85. Some mistake. Okay, let's do it again. Maybe the first value. Okay, so it is equal to the this value minus.
Excuse me, that wasn't the value of the x1 in presentation. Can you open the presentation?
Presentation?
Yeah. The x1 value should be in the next slide.
Oh, it is on the next slide. So I was correct. Yes. Okay, that's correct. All right. So yeah, it's almost the time actually. So anyway, so we will continue this topic in the next lesson after the quiz, if we have time. If not, then maybe in the next week. Okay, so then we have